Okay, now we're ready for arc length of a function. And so what's meant by arc length? Well, if you've got some function like this, let's say, and you wanted to know, if you took like a string and you just matched it all the way here, and then you took the string off and you measured it, that would be arc length. So how can we approximate a curve if we're not have a piece of string, or if it's on a piece of paper, right? It's not the actual one. What we could do is what we do with about everything is we could break it up into little sub-intervals. So if this is like from A to B, let's say, okay, or we wanted to know this arc length, we would say, okay, let's start from this point and go to this point. Maybe not A to B yet. Let's say we just want to go from this point to this point. And then we say, wait, let's break it into sub-intervals like we do just about everything. Okay, so we'll say, let's break this guy up. Here, 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 here. Okay, here's some breaks in our curve. So if we break this guy, and then we connect the segments, okay? Well, it is pretty easy to calculate, and here's the last guy. Okay. It's pretty easy to calculate straight the area underneath straight curves, polygons. Okay. Oops. Okay. So what we would do is approximate it this way. We could find the area of this pretty easily, and the area of this, and this, and this, and this, and so we're going to approximate it that way. But if I blow up one of these, so let's take this first segment, and let's say, okay, here's the arc itself, and here's what we're taking the area underneath here, right? What if instead of just, if I add more sub-intervals and make these smaller, and smaller and smaller, what would happen? How would that benefit us? Well, instead of breaking it here, let's break it into, instead of one big piece, let's split this in half. So maybe I would draw another point here, another point here. Instead of this big arc, this would give me this one, and this one, and this one. So you can see that the green pieces are a lot closer to the actual curve itself. So as usual, the more sub-intervals we take, the more accurate our estimate is. And so if we take more and more, the better and better we get. So the blanks on your sheet say the length L of the curve is approximately the length of this polygon here, okay? And the approximation gets better as n increases, or as the number of sub-intervals increases. So that's how it goes. Then we have this arc length formula that they gave us, which is really good. It says if f prime, the derivative, is continuous on A to B, then the length of the curve y equals to f of x is given by the integral from A to B of the square root of 1 plus f prime of x squared dx. The derivative of y squared is what that is. So sometimes we write this in different ways. We might write this as a dy dx squared, or we might write this as dx dy squared, depending on how we're working with the curve. So you might see it occur that way. Let's do a quick example and see how this goes. The first example I think is really good because it gives us faith in the formula that we're using. It just shows that it's a good formula, and we're going to prove it, sort of. That's not really proof, but we're going to verify that it works for this. And we're going to do it on a curve that we can actually calculate the length of. We're going to do it for a line, which we know how to calculate the length of. So if we've got this guy right here, example 1 says, find the arc length, use the arc length formula to find the length of the curve. Y is equal to 2x minus 5 from -1 to 3. Okay, so the arc length says this. The length of the curve is equal to the integral from -1 to 3 of the square root of 1 plus y prime squared dx. So this is y. What is y prime? Or dy dx, however we want to call this. This is, if we take the derivative of this guy, it's just going to be 2. And if we square it, we get 4. So what this ends up being is 2 squared, which is 4. So 4 plus 1 is 5. So we're integrating 5 with respect to x. All right, we integrate a constant. It just is that constant times x. And we're going to evaluate this from -1 to 3. So the length of the curve is going to be the square root of 5 times 3 minus the square root of 5 times -1, or 3 times the square root of 5. A negative times a negative is positive, plus the square root of 5, or 4 times the square root of 5. This is what the arc length is right there. Okay, cool. Now, we are going to verify this by just calculating it with other methods that we know. So let's draw a quick sketch of this line. This is a line with a slope of 2 and a y-intercept of -5. We're down here at -5. Going to rise 2, run 1. This is kind of what our line looks like right here. Okay, so here's our line, 2x minus 5. Now, we want to calculate the length of this line from x is -1, so down here, till x is 3. 1, 2, this is 1, 2, 3. -1. Okay, so from here to here about. Okay, so this point is -1, -7, if we plug that into 2x minus 5, and this point is 3, 1 is what it ends up being, if you plug that into the line. So, now we're just going to use the distance formula that you learned probably years ago. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So, this is for the points x1, y1, and x2, y2. So, these are our points. So if I say 3 minus -1 is 3 plus 1 is 5 squared. No, 3 plus 1 is 4. 3 plus 1 is 4 squared. Okay, and then we have 1 minus -7 is 1 plus 7, or 8 squared. The distance between these points is going to be the square root of 16 plus 64, or the square root of 80. But 80 can be rewritten as 16 times 5. And you can take the square root of 16, which is a 4, times the square root of 5. And so we find out that the distance between these 2 points is 4 square root of 5. And we calculated using the arc length formula that the length of that curve from -1 to 3 is 4 square root of 5. So that's a nice example to kind of say, okay, this is a decent formula, we can use it. Also, if you look in your book on page 544 to 545, there's a really good explanation of how they derive this formula. So that is even more faith that you can have in this formula. Okay, let's do example 2. Example 2, we're going to set it up. The tricky part to this is the integration is it's just a little bit involved. It's not terrible, but it's one of the integrations that you sort of have to think about a little bit. So here we go. Let's go ahead and do example 2, which looks like this. It says, find the exact length of the curve y is equal to x to the third over 3 plus 1 over 4x from 1 to 2. All right, we're going to use this formula. So let's set it up here. This is going to be, we're going to integrate from 1 to 2, the square root of 1 plus this guy squared dx. Okay, so let's take, first I'm going to rewrite y in a form that I'm ready to take the derivative of. So this is going to be y is equal to 1/3 x to the third plus 1/4 x to the -1. So y prime will be x squared minus 1/4 x to the -2. So this is y prime. And so we're going to say, we're going to square this guy. X squared minus 1/4 x to the -2. So if we square this guy, I'm going to be over here, I'm going to do it a little carefully. Y prime squared is going to be x to the 4th minus 2 times 1/4 times x to the negative 2 times x to the 2 plus 1/4 is squared is 1/16, x to the negative 4 is what I get when I square this guy. X to the negative 2 times x to the 2 is x to the 0. So this is really just a 1. So what this ends up being is x to the 4th minus 1/2 plus 1/16 x to the negative 4. That's what I get when I square this guy. So this becomes the integral from 1 to 2 of the square root of 1 plus x to the 4th minus 1/2 plus 1/16 x to the negative 4 dx. Okay, here we go. Now 1 minus 1/2 becomes a positive 1/2. So I'm just going to simplify it like that. And then I'm looking at this guy going, I'm not sure what to do here, but when I start looking at this, I might write this as 16, I might move this x to the negative 4 downstairs and rewrite this as 1/16x to the positive 4. So let me fix this. And then I might just say, let me see what this looks like if I get everybody have the same denominator of 16x to the 4. So let's do that one. Excuse me. 16x to the 4th is what I'm going to get here. Okay, so this is currently over 1. To get a denominator of 16x to the 4th, I had to multiply 1 times 16x to the 4th. So I have to multiply the numerator by 16x to the 4th, which gives me 16x to the 8th. All right. 2 times 8x to the 4th would give me this. So I have to multiply 8x to the 4th in the numerator. I didn't have to multiply anything, so that stays like that. Now when I stare at this guy right here, I realize that this will factor. And this is actually a perfect square. And so this can factor into 4x to the 4th plus 1 quantity squared over 16x to the 4th dx. Now, whenever I factor, I multiply it in my head or on paper to make sure. So that's 16x to the 8th plus 2x to plus 2 times 4 x to the 4th plus 1. Yep, that works. Now, I can also take the square root of 16x to the 4th. So if I do that, that could be written as 4x squared, quantity squared. Okay. And this is, I have this terrible habit. This is under the square root. This is under the square root. I shouldn't have left that off. The dx is not under the square root. That's not under the square root. All right, so let's just look here. The square root of something squared is just the something, whatever that happens to be. So right here, the square root of this squared, well, here's something else. Right here, a squared over b squared is the same thing as a over b squared. We got to remember this rule. So I have this thing squared over this thing squared, so I can think of it as this whole thing squared. And the square root of something squared is just the something. So this becomes the integral from 1 to 2 of 4x to the 4th plus 1 over 4x squared dx. All right. This is a long one, but we're getting somewhere finally. This can be integrated very simply by separating it in two terms. Now that I just have a monomial in the denominator, I can divide it into each of the numerators. This becomes from 1 to 2, 4x to the 4th divided by 4x squared is x squared. And then plus 1/4 x to the negative 2. And this integrates, now this is very simple to integrate. This becomes x to the 3rd over 3 plus 1/4 x to the negative 1 divided by negative 1, which will make that negative, evaluated from 1 to 2. All right, let's bring it up here. That's going to be 8 over 3 minus 1 over 4 times 2 minus 1/8 minus 1/3 minus 1/4. Okay, so that's going to be 8/3 minus 1/3 is 7/3 minus 1/8 plus 1/4, which is 2/8. So it's 7/3 plus 1/8. And we could get a decimal by putting that in our calculator. All right, that's number 2. Number 3 is not all that hard, but it does involve trig, and sometimes that's good for people to see that one. So example 3 says to find the arc length for the curve. Y is the natural log of the cosine of x. All right. From 0 to pi over 3. Okay, so y is the natural log of the cosine of x from 0 to pi over 3. So we can use our nice formula there. The length is equal to 0 to pi over 3 of the square root of 1 plus the derivative of y squared. All right. So if this is y, y prime is the derivative of the natural log of cosine is 1 over the cosine times the derivative of cosine, which is negative sine x, because this is chain rule, right? So this becomes, y prime becomes negative sine x over the cosine of x, which is also can be thought of as negative tangent of x. All right, so this is negative tangent of x is what goes right there. But a negative times a negative is a positive, so this is really tangent squared of x. All right. So we get the square root of 1 plus tangent squared of x. But 1 plus tangent squared of x is a Pythagorean identity, so this is secant squared of x. And the square root of something squared is just the something. So this just reduces to 0 to pi over 3, the integral of the secant of x dx. When we integrate the secant of x, this is a little bit of an awkward one, but it's the integration of secant of x is the natural log of the secant of x plus the tangent of x in absolute value signs. And we're going to evaluate from 0 to pi over 3. So here's my unit circle. This is pi over 3, which has the coordinates of 1/2 square root of 3 over 2. And this is 0, which has the coordinates of 1, 0. All right, so this becomes the natural log of the absolute value of the secant of pi over 3 plus the tangent of pi over 3 minus the natural log of the absolute value of the secant of 0 plus the tangent of 0. All right, let's see what happens. The secant of pi over 3. This is pi over 3. The secant is the reciprocal of the cosine. The reciprocal of 1/2 is 2. The tangent of pi over 3 is sine over cosine. So that's square root of 3 over 1, or square root of 3, minus the natural log. Okay, the secant of 0 is the reciprocal of the cosine. 1 over 1 is 1. The tangent of 0 is sine over cosine, which is 0. The natural log of, 1 plus 0 is 1. The absolute value of 1 is 1. The natural log of 1 is 0. So this reduces to the natural log of, and really we don't need absolute values here because this is a positive value, 2 plus the square root of 3 is what that ends up being. And so this is approximately equal to 1.316. That seems, okay, so that is number 3, had a little bit of trick. Okay, let's do 4, which involves the St. Louis Arch, which is kind of cool. The Gateway Arch in St. Louis was constructed using the equation y is 211.49 minus 20.96 hyperbolic cosine. How often do we get to use this? But it was constructed using a hyperbolic cosine, which is cool. for the central curve of the arch, where x and y are measured in meters and the absolute value of x has to be less than 91.2. Estimate the length of the arch to the nearest meter, and we will use our calculator for this one because it's nice. We're going to use it for this one. So here we go. What they said first was that it's between x has to be, the absolute value of x is less than or equal to 91.2. So let's look at that absolute value symbol and remember how that works really quickly. If I can erase this, for heaven's sakes. All right, here we go. If we have the absolute value of x, it's got to be less than or equal to 91.2. Boy, that barely even shows up. Then, when you take off the absolute value signs, this becomes negative 91.2, 91.2, and so that gives us our limits of integration. Negative 91.2 to 91.2 is our A and B. The square root of 1 plus the derivative of y squared dx. Okay, here we go. So, what they gave us was that y is equal to 211.49 minus 20.96 hyperbolic cosine 0.0329 0.03291675x, right? All right, there we go. So I have to take this guy's derivative. All right, the derivative of 211.49 is 0, so that's nice. And then we have minus, this constant in front, minus 20.96 hyperbolic cosine of 0.03291675x. Oh, wait. The derivative of hyperbolic cosine is positive hyperbolic sine. So the derivative of this is 0. This is the constant. Derivative of this is sine, hyperbolic sine of this. Chain rule times this. Times, and I'm going to multiply this number times that. Times 0.03291675. Okay, so let's set up this integral from negative 91.2 to 91.2 of the square root of 1 plus this squared. So if I multiply those two numbers together, I get negative 0.6899539. And this is times the hyperbolic sine of 0.03291675x. Okay, now, with our calculators, we're going to calculate this. So, I'm using a TI-84 plus. So, all right, so if I turn it on, what I get here is, to get my integral, I want to hit math, and I'm going to go down to 9, and that gives me the integral here, okay? And then I'm going to say negative 91.2, 91.2, and then I'm going to get my square root button, hit your your second and the next square, which gives you the square root. Okay, I already messed that up, so let me try that again. Negative 91.2, 91.2. I want to hit the square root. Now I want it to look like that. Okay. And then I'm going to enter 1 plus parentheses negative 0.6899539. And now I have to find the hyperbolic sine. This is where you find it. It's in the catalog button. So you hit the blue second button, and then you hit catalog. And so you can scroll all the way down till you get to hyperbolic sine, but if you want to shortcut it, you can hit your alpha button and then your S. And for some reason I have to do that twice. I'm hitting the green alpha button, and the S is located above the LN, and then that skips me to the S's, and then I'm just going to use my down arrow button until I get to the hyperbolic sine, which is right after sine inverse on mine. Probably yours too. So I hit enter, and then I'm going to say 0.0329 291675x, close parentheses. And then I'm going to close the parentheses and square it. And then I'm going to say with respect to x, and then I'm going to hit enter, and it's going to calculate it. And it tells me that it's 451. That is approximately the length of the arch is 451 meters long. All right.